When you learn your derivatives, there was a function. Function was evaluated at x. Derivative of a function at x was also evaluated at x. Second derivative was evaluated at x. So you might think derivatives are no big deal. There is a function. Derivative function is another function, etc. But when you do them on a discrete lattice, you realize derivatives are profoundly non-local operators. And I'll illustrate this by something that you might not know, but it might look familiar to it anyhow. If you don't know it, just consider it a matrix equation. If you do know it, it'll remind you of something, quantum mechanics, quantum field theory. So when you solve linear problems, often you use green functions. You use this in electrostatics, for example. And in some subject, these Green's functions are called propagators, for example, in quantum field theory. But for us, they're just matrices. So look at the matrix, which has the Laplacian, in other words, the second derivative in the numerator, and then it has some coefficient, often called mass, times unit matrix, which I'm not writing downstairs. Now, this is a matrix, it has some entries in it. This is a number. So I can always make this number larger than enters in this matrix. So I can always pull it out. And consider unit matrix minus 1 over m squared Laplacian. So this is just an n by n matrix on a lattice that has n sides. And remember, a function of a matrix is a function just like ordinary functions were. So one thing I can do is I can use the fact that this is a small number compared to 1 for sufficiently large parameter m squared, and expand this as a geometric series, so just in powers of this number, but now it's a matrix. I'll pick up m2 to the kth power, and then delta to the k. So as you know this matrix, we can evaluate this propagator matrix by looking at the powers. So for example, if k equals 1, I have my usual Laplacian. But if k equals 2, I have to evaluate the square of Laplacian. That's easy. If you remember, Laplacian was a matrix, a triagonal matrix. Is minus 2's on the diagonal, and then 1's above and 1's below, and 1's in corners to assure periodicity, periodic boundary condition. It's a matrix, so we know how to compute the square of the matrix. And pretty soon you'll get hang of these computations, but basically if you have a tridiagonal matrix, you will find out that you get something that has 5 diagonals. So it turns out to have 6's on the main diagonal, minus 4's just off. Then you have 1's 2 diagonals away. And so it marches on. So there are these 3 diagonals below, including the central one. All in all, there are 5 diagonals. Lots of zeros as usual. But then to assure periodic boundary conditions, in the corner here, there is a -4 that just this guy shifted. And there is a 1. And same down here, 1, 1, -4. And you continue computing these guys. And what you realize, you have all powers of them. And higher powers have more and more diagonals. And this always becomes a full matrix for any finite size. So this actually is a very nasty calculation. Started as something very innocent. It was basically almost a diagonal matrix, but it was just a little bit off diagonal. Little stuff on the side comparing the point with its left and right neighbor. When you try to compute the function of that matrix, the simplest possible function, you get a totally non-local operator, meaning that it's a matrix that connects every side to every side because it's non-empty every place. That's a big trouble.